Hello, everyone. Welcome to the final intern talk today. Today we have Ben, who was working with us all summer, really worked really hard on a new problem. So it's my pleasure to introduce Ben, who's a PhD student at CMU. He works under the supervision of Professor Bhiksha Raj. His current research is focused on machine learning for audio. And previously, he was a staff researcher at ICSI at UC Berkeley. And he has done a lot of work on audio understanding and multimedia problems in the past. And today he's going to talk about his final internship project on a cross-modal audio search engine based on joint audio text embedding. So with that, please welcome Ben.
Thank you, Shuai, for the introduction, and thank you everyone for coming here. I know that everyone is busy, so I appreciate your time. Let's start with presenting and introducing the topic. First, we have that there are many multimedia and audio recordings that are captured every day. All of these recordings carry information. Specifically in this talk, we're talking about the acoustic information. There are sounds, there are soundscapes, there's information that tells us what's going on in these recordings. And there are recordings that are captured and shared in social media, for example, where people typically will add some words or descriptions to describe what's going on in the content. But on the other hand, there's also recordings like from Amazon Echo or Alexa, and these devices, also surveillance camera, customer services, recordings, etc., where no one takes the time to label or annotate what sounds or what audio it's in the content. So if we have these recordings, it's very complicated to do search and retrieval. So what people typically do is to approach the problem with either text or audio similarity. So let's say, for example, that we have a query on the left, and we have a pool of information of audio and associated labels on the right. If we take the text query cat, we are going to be able to retrieve the first and the third recording because they are properly labeled. In the same way, if we have an audio that corresponds to cat, we can retrieve the first and the third and the last one, even though the last one doesn't have the label of cat, but acoustically they are similar. On the other hand, if we pass an audio and then we are able to retrieve the green audio from the pool, but then in this case we don't have tags, right? So in this case we use acoustic similarity, but we don't have tag associated to that sound, so we don't know what is the content of the sound until we actually listen to it. This might be easy for certain sounds like cat, but there are some other acoustics and sounds that are more complicated to decipher without some context. And there's also people with disabilities who cannot listen to the audio and infer the label. So one solution that is common in the literature is to generate text metadata for these audio recordings using automatic speech recognition or sound event detection. That is that there are labels for sounds assigned to segments of the recording. Now, what we propose here and what we tried this summer was a cross-modal approach. And we aim for two main goals in this approach. The first one is to map audio and text into the same shared latent space. And that will benefit us because then audio and text can be comparable. So if we pass a query that is a text or an audio recording, we can map it to that joint space and find the neighbors that correspond to that recording. The second and most important, I think, is that the shared space should preserve semantic similarity between the text and the audio. So typically, as I was saying, the approaches will be designed separately, text and audio. But here we want to combine both meaning the acoustic similarity and the semantic similarity. For example, if we have the words violin breaks and violin plays, those two are semantically speaking in terms of language similar because they refer to a violin. But if we think of the acoustics of the sounds that they will produce, they are different. So we hope and we aim that this joint space will find a middle point to preserve the similarity of the text and the audio at the same time. Okay, so the rest of the talk is about the approach that we follow to create this joint space and how well those joint representations work for classification and also for retrieval. When it comes to related work, we selected mainly three papers, and the first one is it described an approach for search and retrieval using text and audio queries. And although this was a fast approach, it was developed in an independent way where text and audio were trained separately, and then at some point they were combined to assign a score and then retrieve information based on those scores. That approach didn't work with out-of-vocabulary words. Then the second approach from Malcolm, he created a semantic space with text, like a hierarchy, and then on the acoustic space, they cluster audio, and then they linked those two spaces. But this approach it's hard to scale because you need to create these associations and clusters. And then on the third approach, we actually look at computer vision, and we found that there's some papers that refer to image and text embeddings, where they try to approach the problem in a similar way that we described. So the approach that we have and that we are going to use across this presentation is the Siamese network. The Siamese network, the overall idea, I'll explain more of the details after. The overall idea is that it will take audio and text, one on each head, and it will you will take positive and negative pairs, and the positive, that means that the text and the audio correspond to the same class, and negative pairs mean that the text and the audio correspond to a different class. So we will use these pairs to train this network, and then at the end, at the top, the loss function is trying to make the two modalities that correspond to the same class to be closer to each other, and the two modalities that correspond to different class to be separate. Then at the embedding stage, once we have this neural network trained, we will be able to feed either audio or text, and then create joint representations or embeddings. So we can see the output of those embeddings as an intermediate feature that considers the text and the audio space. So what we typically will feed to the neural network are features. In this case, for example, we used audio features, which are MFCCs, are a good standard feature for this task. And since we needed a vector, we basically computed the mean of the entire MFCC matrix corresponding to each of the audio recordings. And then we created mean vectors across time. And the same, similar approach with the text. With the text, we use word-to-vec. Word-to-vec, if you're not familiar with that, is a technique to convert one word into a numerical vector. But those vectors preserve a semantic similarity. So words that are similar will exist in the vectors with a close distance, and words that are different will exist further apart. So the dimensionality that we use for our audio and text features was 300. And this is basically the setup that we use for most of our work. Then the input and the configuration of the Siamese network was the following. First, we passed the features, as I described before, and we assign a 0 or 1, depending if we are passing negative or positive pairs. Then this network is basically the same. That's why they call them Siamese. It's exactly the same, and they share parameters. And it was a simple DNN, and the output was 1024. That is the dimensionality of our embeddings. Then once we have the embeddings from audio, embedding from text, this is training time. We're going to pass it to the head, to the part where we do to enforce the similarity between modalities.
So
typically,
the parameters you said in the previous slide were the final parameters you picked after doing other experiments. Like, why did you pick those 1024? Because they perform best, or
where did I perform the
1024? Why was the network?
The network.
Oh yeah, the network parameters. Yeah, so I basically carry on some tuning with started with one layer and then changing a number of nodes, a number of layers in powers of 2, After spending a reasonable of time tuning, this was the best performance, but there's more explanation to be done. Okay, so this is the most important part of the neural network, because here the leads are to basically work with this combo, the contrastive loss and the L2 distance. So the goal of this contrastive loss is, as I say, to enforce that pairs that correspond to a similar class are closer and separate a different class to be separate. And it does it using the part that we see on the right, which is a margin. dW is the distance for similarity. And when we have similar data, we want the pairs, we want them to be close within the margin M. M is a hyperparameter that we also tune. The problem is that this actually didn't work for our data. So we try some other similarity techniques and distance, and also another loss function. So at the end, the combination that performed the best was the binary cross entropy, which also has a binary setup. But now the distance, we use the exponential minus L1 or L2. The best one was minus L2. And here, you have to think that the L2 and L1 as they have an unbounded score, right? So if it's very similar, it's a small number, and if it's very large, it can grow very high. But if we use the negative exponential, then we force the distance to be a number between, remember that if you look at the plots, it looks like this, the exponential with the negative inside. So if they are similar, we're going to have 1, and if they are different, they're going to tend, it will be a number close to 0. So now we have a probabilistic framework there. And this one showed the best results that I'm going to show later in a different slide.
What is the role of the second parameter in BCE? The first is the divergence.
In BCE?
Yes.
So
1 minus yi logarithm of 1 minus dw.
Yeah, so if you get so remember that we're passing pairs with 0 and 1. So one will take care of one class and the other one will take care of the other class.
So yi can be 0 or 1?
Yeah.
So if yi is 0, the first term is 0, only the second loss would be used. And then if yi is 1, then the
it's correct. Binary. Okay.
Yeah,
okay,
it's a binary setup. It's binary for both of them, right?
Okay.
Because we work with pairs 0 or 1.
So can you explain why did we
Which
use...
is 0 and 1.
So can you explain why did we use exponential, why not hyperbolic tangent, tan h function to do the compression?
Yeah, so in this case, as I was saying, we chose this one because it gives you a number from 1 to 0. But we could also use the cosine similarity or any other combination, but we just try these combinations, right? But certainly something else can be explored for the distance and also for the binary setup in the loss function. Yeah, but there's no specific reason why we shouldn't try the other ones. So this is the combo that we chose. And then, so now I just explained how we train the network, and now let's go to the data and the experiments. So the data that we use, this is a dataset that was released this summer. And it contains audio recordings corresponding to free sound. Free sound, is if you're not familiar, is basically like a YouTube for audio, where we can find sounds and tags, and users upload their recordings. We have 9,000 recordings, and the duration is up to 30 seconds, single channel. Now, for the text, all of these audio recordings are associated with a text label, which were chosen from the audio set ontology. It's a hierarchy of 527 classes. But for this dataset, they only chose 41 from different categories. Some of the class examples are these ones that we have that can be instruments, sounds of animals, sounds of humans, sounds from just everyday life. And we explored using the text with single class labels and also simulated noisy text by adding random Gaussian noise with 1 or 2 sigma. We'll explain this a little bit more in the future slides. And then for classification and retrieval, we try these two models, statistical models, but most of the work is done with nearest neighbor, basically because, well, let me show the next slide. Yeah, sure.
It's 30 seconds, and then you average all the features within those 30 seconds.
Yes.
That's
Yeah. So if we have 300 milliseconds and then the audio is a matrix that, depending on how you extract it, but if it's 300, it's represented 300 milliseconds, we just average over time. And then we get just one single vector for each audio recording.
I didn't get the connection between free sound and audio set.
Right, so the authors of the data set, what they did is that they chose 41 classes from audio set.
In free sound?
No, first they chose...
Audio set.
Right, so, but just the labels. So they took the ontology from audio set, not the data, just the ontology.
Oh.
Text, audio and text.
Exactly.
Okay.
And then they used those classes to download audio from free sound, and then they sort of like clean the data, and
So
then...
you do have a description of the free sound files, but using the dictionary from audio set.
Exactly.
Okay.
Exactly. So the goal they wanted to... If you use audio from video, it tends to be very noisy, and it's harder to clean. And also, the rest of the metadata is not precisely associated to it, right? So it's a more complex problem. This one, they try to clean the whole setup to make it easier to explore.
And the labels?
So the label is from the audio set. So the audio set has this ontology. It has 527 labels. They chose 41 based on whatever system they have. And once they have the label, they went to free sounds. They queried those sounds, collected 9,000 recordings, distributed across the 41 classes, and then that was the data set.
So pretty much each free sound file carries one or more labels from that 41, a group of 41 classes.
Yeah, good question. So audio set actually has a multi-label problem. Here they ensure that there's only one of those 41 classes.
So each file carries one class?
Carry one annotated class. There might be some other sounds there. So let's say that you have one recording with drums. It will be labeled as drums. However, there might be a violin playing the... well, in this case, we have violin. Let's say there's a bird chirping. That will not be annotated.
But if you have drums and violin and you label it as drums only,
yes,
whichever is dominant.
Yes, the dominant.
And for this classification, is this came with free sound, or you did the labeling by yourself by running the audio set classifier?
No, this was done by the people who...
Okay.
This is a decase data set.
This is a decase data set which already was defined.
Oh,
it was collated by actually the people who are in charge of free sound and the people who are in charge of audio set.
Okay.
So they basically team up and came up with this one.
And they had one reviewer to annotate.
Yeah, so they also have they do a revision. I don't know if they don't say in the website. I don't know if it's just one or they have 3 of them,
Okay.
and then they assign a number of confidence whether they actually detected a sound inside the recording or not. Most of them are very properly verified and actually accurate, but not all of them.
So there are high chances that your data are challenging to begin with.
Exactly. Good. So this is the data. So the first experiment that we tried was to see how well the embeddings from the Siamese actually work in comparison to just the handcrafted MFCC features, audio features. And what we did here only for this experiment was to train the Siamese network only using audio pairs, not text involved. So we will use pairs of audio corresponding to the same class or pairs of audio corresponding to different classes. So we have our training audio, we computed our MFCCs, and then we train the Siamese network. Then in the embedded stage, we pass all our audio set, our 9,000 recordings. We computed MFCCs, and then using the trained Siamese network, we computed what we call the audio solo embeddings. So these are embeddings that come, intermediate features or embeddings coming from the trained Siamese network. In the evaluation stage, we treat this first as a classification problem, and then we use our embeddings that we created and do a classification task, train and test independently. The performance that we got here comparing the handcrafted features and the embeddings is the following, and there are 2 main takeaways here. I'll help you go through the slide. One is that the MFCCs and the embeddings from the Siamese network, they were performing comparably. That means that the discriminative power of the embeddings was comparable to just the handcrafted MFCCs. The second is that we use KNN and we tune the K parameter, and also we use the SVM linear and we tune the parameters inside. We're basically seeing that the performance with the handcrafted features and the embeddings were comparable. We decided to pick the KNN because it provides a better framework for the idea of having a neighborhood of embeddings. That way it will be easier to present the retrieval results later on.
So, let me understand the number. You have 50-ish% classification accuracy on 41 classes.
Correct.
Using a 9,500. Why did you did not use something more sophisticated than SVM or KNN, like a DNN network or?
We use that also. It's
Yeah.
similar performance.
Serious?
Yeah. So but
It wasn't that good. And
so I tried an MLP with 2, 3, 4 layers, and it was performing similarly to this with the audio embeddings. The problem is that one was taking longer to train, and also there's so many parameters that can be tuned that we just stick to these two because it's easier to tune. And again, the performance was comparable. I'm sure that if we will try a more complicated neural network instead of these two classifiers, we can improve performance. Yeah.
Okay.
I had one question about the MF. So you chose one MFCC vector for the entire sound clip, quite
Correct.
averaging. Did you think about other ways of summarizing those MFCC vectors?
Yeah. So we can do super vectors or I vectors, any other approach, certainly.
Because the only data about the dynamics of the signal you have is averaging the deltas and deltas.
Right.
Also.
Right.
It gives something, but not much.
Right. Yeah. So there can be better ways to represent the matrix as a vector. Actually, later on we use better features to show, and we will show the performance. But we also
From 2.5 chance to 51%. Hey, it's something.
And the
Yeah,
goal
that's
of
true.
the picking the classifier was not an important point. The point which we're trying to make here is the embeddings, do they perform the same as the raw features?
yeah.
So it looks like your features are pretty efficient, right? If DNN was also performing similarly, it looks like your features are.
Yeah, consistent across
So
classifiers.
if you're lacking something, that's futures.
So the bad thing here would have been that the dark blue line were 20% and the light blue line were 50%. Then that's bad. That means that the Siamese network is not doing well.
Right. Then we cannot
That's
justify.
what this shows.
Exactly. We will not be able to justify, at least in this context, going through the extra effort of the computing the embeddings if we cannot be the simple MFCCs. Anyway, so now we have the joint approach. In this case, now we actually use audio and text. First, we take our audio and text, the training set. We compute our vectors of MFCCs and our word2x for text, and then we train the Siamese network the way that I described before. So now we pass all our audio recordings, compute the MFCCs, and compute the audio joint embeddings. Right? So these joint embeddings, again, come from a trained network that was using audio and text. We did the same for the text. For the text, we computed the text features, word2vec, and then we pass it through exactly the same trained Siamese network, and we compute our text joint embeddings. So now we have intermediate representations for the audio and for the text. And then the same setup where we have a classification task, but now we're going to show the cross-modality experiments, cross-modal experiments. So first, here what I want to show is how the handcrafted features compare to the joint embeddings. In the top row, we have training only on the means of the MFCCs, and then test them on the means of MFCCs, train and test faults. And then on the right, train only on the text, which are the word-to-vec vectors, and train on the word-to-vec and test on the MFCCs. So the performance is 49.7, which is similar to the bars that I showed you before. And then 2.4 is a random performance because basically the features are independent, right? We have MFCCs and word-to-vec. They are unrelated. So we expect it to have the...
So literally you try to synthesize the sound from
Text.
Exactly.
It's not possible. So that's what we're trying to solve.
Well, except for those onomatopoeia words, right?
Yeah, potentially. Which we have in the classes.
But seriously, if you had only those words, you should get a better than chance.
But we don't have those in the class.
Yeah, okay. Fine.
Yeah. Anyway, I have to think about that one. That's true. Anyway, so these are the results when we actually use the joint embedding. So for audio joint embeddings train and test, we get a slightly better performance. And then for embeddings of text, so we train the nearest neighbor with embeddings from text, and then we test it with embeddings of audio. And now that the performance was not random, was actually comparable that if we would have just an audio setup. Okay. So this is one of the main results where we actually show that cross-modal embeddings can actually be used for train and test.
So, question, does that mean that the embedding represents better the audio, or is based mostly on audio,
Yeah, so it seems that the embedding improve, and my intuition is because now we're adding the text information, so we're basically adding another modality on top, and that's helping us improve this one, and of course that one has the help of the audio when we train the Siamese network. So now we are making embeddings comparable, which was one of the main goals.
So to answer one little more addition to the answer is, the test was on only audio here. You could also test on only text features. The rows could be test on text in addition to that. So ideally, we would want all four of them to be 50%.
I went to the second part of the table now.
Yeah, so we'll show that later. So there is some complication in that, but we'll show later.
That's the complicated part.
So if it's all 50%, then it's perfect. That's what we want. All four of them should be 50%.
Exactly. That would be the ideal case.
So can we prove that the embedding is or isn't biased towards the audio space versus the text?
Yeah, if it's all equal, then you can conclude that.
Yeah.
Right.
Yeah,
We'll see.
We'll see, but that's a good question because, I'll touch that topic in a few slides. So, in order to compute these results, I just want to show a couple of interesting things when it comes to training the Siamese network. And one is that this was using the audio joint embeddings, audio with audio. And then we can see how the number of pairs that we use actually affected the performance. Depending on how much data we have, this can explode. So it's important to know the minimum amount of pairs that we need to do this training. Then these are the results, also again with the audio joint embeddings, and this is how the performance differ or varies with the different combinations of loss and similarity. We ended up using the one on the bolded. Okay, so now we go to the text part. So, before that, I added this extra row here, which the only difference is that now I added the better audio features. They come from a sort of a complex CNN architecture using low melt frequency features and then pass to the CNN. And then it has 7 layers, convolutional layers with max pooling, etc. And then the output were these features that we use, that they were also a vector, that we pass to the Siamese. And basically, yes, if we have better features, better audio features, we can improve the performance, right?
Is that CNN from DK's winners?
No. No, this actually is from a paper that is in submission. Is from a few members of our group, and their performance on audio set was comparable to the state of the art.
So we could use the decays of the audio sets.
I think
Yeah.
that's what Harry used, and I'm curious to.
Yeah, so what we use this because we had this access
Yeah.
to this.
Yeah.
So there's one author who participated in both papers, the one from Harry and this one,
Okay.
but it's not this first author.
So that is maybe a newer version of.
Yeah, exactly. Anyway, but the point is that if you improve your features, you also can improve your embeddings. And then, so now let's go to the cross modality with text.
And you should explain what is the catch in the text. Why is this text not the ideal text?
Oh yeah. So there's one thing that I didn't touch too deep. So the text here. Remember that we have 9,000 recordings, and we have a text label associated to each of the recordings. We have 41 classes. So the text is basically the same text for the recordings in training and in testing, right? Does that make sense? So that means that the data that we have at training time, we also have it at testing time. So what we will expect here is that, again, this is a random number because we're training on audio and testing on Word2Vec. These are completely independent or related features. And then we're going to have 100% there because we have the data, the same data for training and testing.
Yeah, just to clarify, so the labels were cat in training, cat, and in testing also they were cat.
Right.
But in reality, they're not like that. The tags are cat, kitten, pup, small kitten, all of that, right? And then the testing tags are slightly different than that. But in our case, in this experiment, they were the same. So that's why we were achieving 100%.
Oh, but you easily can pre-process the text. This has been done. It's a routine processing in speech recognition and
Yeah, but if we do that, we won't get 100%. What I'm saying is if there is noise in the text tags, it won't be 100%. So
Right.
that's to answer why we have 100%.
Exactly. Thanks. Exactly. So then, under this premise, we wanted to see how well the joint embeddings perform, given that we do have the same text in training and test, but we're passing it through the embeddings first, so the Siamese network first. So we were able to achieve 100% in both. Now, this one, we're training with audio. We're computing audio features with audio text Siamese. So we actually do not, we see the text, the label, indirectly when training the Siamese, but not directly because it's not in the training. Right? However, we still achieve 100%. And then in the other one, it does make sense that it's 100 because we have the joint embeddings that are exactly the same in train and test. And this trend is the same when we use better audio features. Now, this is
real case.
now a more real case. So a more real case. So we added noise we added simulated noise to the text. We generated random Gaussian noise with 1 and 2 sigmas. So that will mean that one sigma is more noisy than the original text features, and 2 sigmas will be even noisier. And the way that we add the noise is that when we computed the Word2Vec embeddings, we add the noise to that vector. And it will be different noise to every single of the 9,500 recordings.
So you don't add noise on the text, you don't alter.
No. So we add on the vectors.
Exactly.
That's a controlled way. We could have just gone wild and changed the text, but we wouldn't know how to reflect in this. So that's why this is the first interview. We're also going to add random text words also eventually. But we'll see that.
Is that a fair
Yeah.
way of adding noise? Because that assumes that your Word2Vec representation maps similar words.
Yeah, so that's how it works. So if you take cat and if you take kitten and you compute Word2Vec for both of them, it's not 0. There is some finite distance, and that distance is small.
Okay.
But if you take cat and if you take bus and if you take, the distance is large. Now, we could add some random words to cat, like cat and a set of text, and then do the Word2Vec for that. But we won't have control on the amount of noise in the Word2Vec.
Yeah, I'm just asking, is that like, I don't know, how does Word2Vec come up with this? Is that just trained on some large database?
Yeah.
It's trained, this one specifically is trained in the Wikipedia, and it's trying to estimate how likely it is that you have a word in a given context.
So is there any reference that says the noise you get, or the distribution you get is somehow Gaussian? Like you take a word like cat and then
No, we just
Gaussian.
assume that it's
there's
Gaussian.
no study.
Okay.
Yeah.
But
no,
we just
But
but
yeah,
leap
it's-
of faith. This
Yeah,
is like the,
Gaussian noise is always.
right. But this is an intermediate experiment, right? Eventually, we want to use
Yeah.
tags.
Yeah, exactly.
Just curious, how does this compute with words that are very similar but very different meaning, like cat and mat, for example?
You mean the score they would predict?
Yeah, the word to back would be like very close because the word is similar, or is there some kind of associated context, like the meaning is very different, so the distance is different?
Yeah, so the similarity, semantic similarity in the text, it will be learned from the context of the large corpus that it was chosen. So let's say an example that I will make of right now is that you will say, I pet the cat and I pet the kitty. So those two are they will happen very often in the same context, those two words. So they will exist in a very close space in the word-to-vec space. When if you compute similarity, you can use any similarity technique, cosine similarity, for example, and it will give you a score from -1 to 1, where 1 is the most similar, they're basically having exactly the same word, and -1 will be very different words. And for example, if you have cat and cats, they will be close, but not exactly the same, right? Cat and kitty, etc. Oh yeah, sorry. Anyway, so where were we? Okay, so we just a noisy. Oh my God. Okay, so
yeah, we can go.
anyway, so we just added a noise here, the way that we discussed, and now we do again the cross-modal experiment. Now I'm presenting this in a different way. So we have the 4 combinations that we show in the table before, and here we have no noise, noise with 1 sigma, noise with 2 sigma. So at least in this and the third case, adding noise didn't really affect the performance of the joint embeddings, but adding the noise where we actually have to test on text, it actually degraded the performance. Now, this can give us an idea of how it could perform if we actually use the tags or some noisy text, right? So this was just to test the extent of the joint embeddings.
Did the audio have noise in it?
No, we did not add any noise to the audio because it was already, they are web recordings, so they are already, the acoustic diversity is quite wide. Okay, so then in summary, just to summarize, this is what we use the joint embedding for cross-modal classification, and now we want to see how it performs with retrieval. So in the retrieval case, we basically have a similar approach. Now we use the best audio features. We use the same trained Siamese network from before, and then we created our audio joint embeddings again. This is a Disney plot, which is basically a mapping of the train vectors, audio train vectors, into a 2D plot. It's like applying PCA to a large dimensionality and just reducing it in order to plot it.
You said Disney plot?
Yeah, Disney, T-S-N-E.
Oh, okay.
I don't know how do I pronounce it. Anyway, so what we did here first is to do a qualitative analysis where we pass a text query. We just define a text query. And then we pass it through the entire pipeline. And then at the end, we have our text joint embedding for that text word. And then we use the train nearest neighbor to see which are the neighbors, right? Let's say in this case we use a text and we want to see what are the audio recordings that are near to that text query. So let me guide you through this table. First, this is for audio vocabulary words, for words that are not in the 41 classes. These are the text query that we use, and those are the retrieved results from the audio pool. So in this case, we have audio joint embedding.
So you bring additional information here from the algorithm for word to text.
Word to text.
Out of vocabulary
Right.
means a label which is not in the
Not in the
41
label,
classes.
Exactly.
But you bring a different additional notation. How close is this to the classes by
Word-to-vec, yeah.
the training of word to vec?
Right.
Because there should be some external information for that.
exactly, yeah. So it's trained on this universal Wikipedia corpus, which captures the whole language,
Okay.
English language,
Yeah.
in some sense.
So that it's out of vocabulary from our approach, but it's in the vocabulary of the word-to-vec universe. Here we use the word applause, literally type the word applause, and then from the pool of audio embeddings, these were the retrieve results. These were the retrieve results, which seems reasonable for applause. For bark, these were the ones that we retrieve. For gunshot, we retrieve these ones, and I mean that the neighbors were an audio that had the gunshot as a label, an audio that had the fireworks as a label, and so on and so forth. But notice that if we would have relied only on the distance of word to vec, just the text distance, we would have retrieved these words. But these are different because we are retrieving based on text and audio distance. Right? So in this case...
Gunshot is related to applause. Just kidding.
In some weddings.
It's close. Yeah.
Oh, yeah.
You know about that.
Yeah. But this means that it's closer from within the 41 classes, right? Not that it's actually relevant to the gunshot. When we use an out-of-vocabulary word like orchestra is not one of the 41 classes. We actually retrieve this, an audio corresponding to cello, audio from violin, etc. When we use a more abstract concept like house, which is also not in the 41 classes, then these are the ones that we retrieve with our approach. And these will be the ones that we will retrieve if we will only look at text similarity. Okay? So, of course, the user can argue which one is more useful in these more complicated cases. Now we do the reverse. We train, we have a text joint embeddings pool, and then we're going to use an audio query. Okay, so that's the reversed problem. So in this case, we have plus and we retrieve a plus. Now, these experiments were using one standard deviation of noise. And the number of nearest neighbors that you choose to bring the neighbors affect how many results you get. So in this case, we, based on the same number that we use for nearest neighbors, which was around 25, I downloaded an audio of applause from Free Sounds, tested it, and retrieved the embedding of applause. That was the closest one to this audio.
You mean the text noise
Text.
one? Oh, okay. Yeah.
Yeah. So now we're retrieving text from a text embedding pool, and we're using audio queries that I downloaded from the web, from Free Sounds. Same with Bark, it also will work well. A gunshot, it didn't bring the gunshot as a word.
You did have a gunshot in the database.
Yes, I
but
did
we
have a
didn't get
gunshot,
it.
but we didn't get it. And if I would use only audio similarity, I will retrieve these three. But our approach with the joint embedding, audio text joint embedding, retrieve these two. Same with orchestra. Again, orchestra is out of vocabulary. It doesn't exist in the 41 classes. So these are the ones that I retrieve, the text embeddings. And if I would have used just the audio similarity, I would have retrieved this, which is, I think both are reasonable. Now, this is using map. For retrieval, typically we use mean average precision, and K means that when I retrieve the three top results, I should be able that in those three results get the right one. So the results look very close to the performance that we have with the accuracy and classification, but these are slightly better because we are considering the top three.
It's pretty strict, right? 3 is...
Yeah, people
Even
also try
Google.
K equals 5, K equals 10
Yeah.
also.
Yeah, K5. I just used K3 because that's what they were using in the literature in this context. Yeah. Of course, if you increase the K, then most likely you're going to get better results, right? Then, so we're almost done here. What was the next step? So we have that the cross-modal retrieval shows some relevant results using the joint embeddings. We have that it also works well with classification. And we wanted to move forward to use it with more complex audio and more complex tags. So just to finalize, we were working on building a pipeline where we will actually use the more complex audio coming from. First of all, we use an AOL database that has a lot of query terms. We wanted to use real search queries. We pre-process with text processing techniques our data set. Then we created a crawler to collect audio metadata, tags, and so on from YouTube. And then this part is very similar to what I just explained, except for this one, we also included two modules, one that is going to generate synthetic metadata using speech recognition and also sound event detection. So that way we can have more tags and more information. And then we compute the features that way that I described before, train the joint embedding, the Siamese network, and then use it for retrieval and ranking. Now this pipeline was complete, but we didn't have time to actually run it, download thousands of videos and recordings and actually test it. We only did some very small testing on this. Anyway, so the conclusion of this talk is that the method enabled the cross-modal classification as well as retrieval using the audio and text queries, and that the retrieval results from the shared latent space seems to preserve some semantic between the text and the audio. I want to thank everyone for your attention, and thanks Microsoft Research and the Acoustic Group for welcoming me here. It was a very nice time, and thank you very much to Shui for mentoring me this summer. Thank you.
Sorry, there are 50 slides with animations.
Oh.
I do know.
I have a very basic question as a very actual model. So you have a basic neural network to encode both the audio and the text. Why do you use the same model to embed like two modalities? I think that's kind of strange. If I do this, I will use like one model to embed the audio and another model to embed the text, and then try to pull them together. But here it seems that you are using the same model to embed both modalities.
Right. So this particular architecture, the Siamese network, works in a way that this base network shares parameter with this one. So this one has to be exactly the same as this one.
So can I understand in this way? So if in the end, if these two models are same, so you want to make sure the outputs, the audio embedding and the text embedding are similar, then because you use the same like base, and then your original audio vector and the original text vector will also be the same, because neural network is kind of continuous embedding. So
let me motivate you a little bit with the problem, right? So think about it like this. In some of these recordings from smart speakers, we have a lot of audio, right? Some of this audio can be annotated. Some of it cannot be, right? Either you can build a search engine using just the audio, you can build a search engine using just the text. But what we are trying to do is we can make use of all of this information to build a richer search engine. That is what we're trying to do. That's the motivation, right? And you're right. You could actually train a network to just extract features, have text and audio in the beginning, and then do the joint information exchange later, right? Mm-hmm. But this is one way of doing it. You can exchange the information with the base layer and then combine them. Combine them in the beginning and just extract a joint similarity function. But you could also have separate layers and then compute a similarity later. But this is more of a constraint problem which will keep the vectors in the same space.
So if the original MCC feature for the audio is quite different from the word-to-vector vector for the text, then there's no way to really make them similar after the embedding.
So
even though they are expressing the same concept.
So the more separate they are, the harder it is to force them to be close to each other.
Yeah, in fact, I also have a work, but on the image and the text retrieval task. So we have CNN to encode the image feature and another RNN to encode the text feature, and then use the perception layer to combine them together to calculate the similarity. And we also use it for image retrieval, text retrieval. So when I see the shared parameters,
So it's interesting to compare both approaches. Both are valid, in my opinion, but I don't know which one works better. So we tried this because we thought we borrowed this a lot from image and text search, image search. People have done that, but the third paper he cited was actually the motivation for this work.
Yeah, so this one, if you treat them separately, you will end up with two networks, one that treats the text and one that treats the image or the audio. In this one, it's exactly the same network to feed audio and text. So you can treat them separately or the same one.
Next question is which one is better, so we don't know.
Yeah, no. Another question, good.
Could an argument be made that maybe if you have a large imbalance in terms of the training data, like you have a lot of audio but very little text, or the other way around, and if you have this, if they share the...
Then it will be harder to train probably.
Yeah, that affects.
So if it's balanced, then it might be easier to train. We don't know that. So that's an experiment definitely to be done. Because I like the idea you said, because RNN might be better at encoding information from the text, and a different network might be better at encoding information from audio, for example.
Yeah, but in the text-to-vec you already lost the sense of sequence.
Sure. Yeah. So if
And
you
RNN is heavily balanced towards the sense of
so
sequence.
instead of using the word-to-vec also in this as part of the base network might help, and train it jointly with this. That might also be it.
Yeah, so we basically abstracted out or separated the feature computation here, which is different from audio and text, but there are some techniques where they actually connect here the CNN, and it's just fully connected here, and this one is also independent, where you need an alignment stage, which needs to be shared by both.
I mean, in a way, if you word-to-vec is already...
doing something.
Yeah, and same with if you use the CNN features, you basically have two neural networks that are separate and then end up...
Exactly, and
but they're not jointly trained, that's the problem. They could be jointly trained.
But I mean...
They can be joint trained, yeah. But I also understand this part. In this way, you need your baseline and to have larger capacity, because essentially you are learning feature embedding on a much larger space. So you are like your input space, a union of the audio embedding space and the text embedding space. But so in this case, if you want to do if you want to have higher accuracy, then your base NN should have larger capacity than the way if you just want to train a base NN on the audio space and another base NN on the text space.
Agreed. So there are a lot of ways of doing this experiment. The way we started is to actually start from the last slide. We collected all these tags and everything. We're not going anywhere. We realized that it's really hard to train the Siamese network to actually converge to something. Then we realized, okay, we should simplify the problem, and this is how we started. And we are presenting the final flow, and it looks more controlled now. And we don't know how the real tags will perform. It might just not work at all. So we don't know. So we're still evaluating that.
I'm not much concerned about the separate training of the two feature extractors. The closer, the more correlated are they, the bigger is the risk of training them separately. But we just mentioned that they're kind of quite different. So two uncorrelated sets, you can train them separately without losing much of accuracy. And we have seen this on other audio tasks as well. And word-to-vec actually brings a lot of prior information.
Yeah.
It's more towards the thing, what is the equivalent of that to audio?
Audio.
Audio-to-vec.
Audio-to-vec? Nice!
Yeah,
I think
in
that's...
fact, in my work, the text to embed the text, we do not use kind of word-to-vec, pre-train the word-to-vec vector. But in our case, we are embedding sentences, so each word is just like
so you basically
one
train the whole
vector.
thing. That's what I'm saying. Right? So you have the word-to-vec within a part of this network.
Yeah, you can think of it.
We can do that, but it's like a big beast again, like I said.
Yeah, we also discussed about converting this into a more complicated network, a CNN, and there's work where actually they take the audio and they also take text for the CNN. Do you need sentences?
Man, this is not of a concern. This is supposed to run in the cloud somewhere where computational requirements are not that very simple.
No, but it's not about computation. I think it's about getting convergence to this.
Yes.
That is really hard. Because if you use a complex network, you don't know where you're going wrong.
Yeah, exactly. All right, thank you.
If you don't have more questions, let's give a round of applause.